In a prior video, we looked at simplifying rational exponents and getting them so that all exponents were positive. Here we're going to look at simplifying radical expressions. So let's look at the top. It says the product rule for radicals, and yes, this is related to the product rule for exponents. But what it says is if you have like roots or both indexes match, and you're taking that root of two different numbers and you want to multiply them, as we see here, two small radical signs can become one large one over the product of those two, and vice versa. So if I have two things being multiplied, remember, not added or subtracted, but multiplied, I can split that into two small radicals being multiplied with the same index. So let's take a look at that. Example 1a, square root of 5 times square root of 7. Since they're both square roots and it's multiplication, I can just combine those under one radical sign through multiplication. Here again, square root of 11 times square root of p is just square root of 11p. Let's continue with non-square roots. Cube root of 3 times cube root of 12, I can say is cube root of 3 times 12 is 36. The key here, remember, is that the indexes have to match. I believe correctly that is said indices, but I'm saying indexes, and you have to be multiplying. Fourth root of 8y times fourth root of 3r squared is fourth root of 8 times 3 is 24. yr squared, or r squared y. Here, sixth root times sixth root, I'm going to multiply what's underneath them under one large radical sign. 10 times 5 is 50. m4 times m is m to the fifth. Now, using the product rule, I cannot do d because the indices do not match. Even though the radicands match, doesn't matter. Because those are not the same index, I can't do it. Now, I could do this, changing them, converting these to exponentials because the bases are the same. But that's not using the product rule for radicals. That's now using the product rule for exponentials, and I'd have to find a common denominator. So it can't be done using the product rule for radicals. Can't do. The only way you could do it is by using the product rule for exponentials. And I'm not going to finish that because we're talking about using the product rule for radicals here. You can do that by finding a common denominator and adding your exponents. Let's look at the quotient rule for radicals, and this has been mentioned in another video. But if you have one large square root over a fraction, basically what it says is I can split that into two small square roots, one denominator, one numerator, each having the same index. So in example 3a, I can change the square root of 16 over 25 to the square root of 16 over the square root of 25, which I can actually take. The square root of 16 is 4, square root of 25 is 5. Now, if you can go from here straight to here, that's fine. Sometimes you can do that if both of those are perfect squares or cubes or whatever you're taking the root of. In this case, though, I wanted to show you that you can make it two small ones. Here, I can split this into the fifth root of x over the fifth root of 32. I can't take the fifth root of x because I don't know what x is, so it remains the fifth root of x, but I can take the fifth root of 32, that is 2. And so I end up with an answer that looks something like that. Here I have the cube root of a negative 8 over 125. Now you have to be very careful when you split this. A negative out in front of a fraction indicates that the negative goes with either the denominator or the numerator, but not with both. So you don't place that negative in both the 8 and the 125. A negative over a negative would be a positive. So to keep my fraction negative, I have to place the negative sign just with one of them. Cube root of negative 8 is negative 2. Cube root of 125 is 5. And here is what I get. Had you decided to place the negative in the denominator instead, you would have gotten 2 over negative 5. Same thing. Both of those are just negative fractions, negative 2/5. This one is tricky. The negative is outside, so it's sort of like an afterthought. So we're actually going to do that negative sign last. So what I have is the cube root of m to the 6th over the cube root of 125. Now I know there's going to be a negative sign added at the end. What's tricky about this is the numerator. I'm going to write the numerator as a fraction. The root here is 3, so it's that. Cube root of 125 is 5, remembering there's a negative out front. But m to the 6/3, that fraction simplifies, is just m squared over 5, negative out front. And this, converted from this, is something that we're going to look at some more of on the next page. So let's look at the next page of your notes, and it says conditions for a simplified radical. 1, the radicand, that's what's under the radical sign, has no factor raised to a power greater than or equal to the index. I'm going to show you that in a minute. It will make sense. The radicand has no fractions. No denominator contains a radical, and the exponents in the radicand and the index of the radical have a greatest common factor of 1. Now that sounds like a lot to remember, but I'm going to sort of refer back to those as we go through examples of each. So how do we simplify a radical like square root of 24? Well, let's quickly, I'm going to write this across the top and then move it back up, and it'll be gone. You won't see it again. But let's quickly remember our list of perfect squares and perfect cubes. So perfect squares: 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, etc. Perfect cubes: 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, etc. Those are the numbers you have to be familiar with. So in this case, we are being asked to simplify 24, square root. So we're going to use two things that you've learned: perfect squares and the fact that a giant square root can be split into two small ones. So what I'm going to do is I'm going to break down square root of 24 into two factors, one of which is a perfect square. So that would be 4 times 6. Now, this next step I'm going to show you can be skipped, but I'm going to show it to you this first time. I know that a large square root sign over two things being multiplied, two factors, can be split into 2. And I also know that because 4 is a perfect square, I can actually take the square root of 4, which is 2, and I end up with 2 square roots of 6. Now, I can get there directly from here without having to write this line. And you do that by, when you break down your number into its perfect square factor, go ahead and take the square root of the one that's perfect and bring it outside, and that leaves me with 2 square roots of 6. It would have done me no good to break down 24 into 8 times 3, because think about it. 8 and 3, neither one of those are perfect squares. I couldn't take the square root of either one. It also doesn't do me any good to break down that 6 into a 3 times 2, because I can't take the square root of either one. So in this case, unlike a factor tree where you keep going till you can't go any further, here you only want to break down into the biggest square root, perfect square number as the factor that our original number has. So let's look at 108. You may or may not know what goes into 108. So those perfect squares are 1, 4, 9, 16, 25, 36, 49, etc. Well, the first thing that goes into 108 is 9. So you might think that I want to break that into 9 times something. But in this particular case, 36 also goes into 108. And you always want to break your number down into the largest perfect square factor, because then you only have to break it down once. It's like simplifying a fraction. You want to use the greatest common factor. Here we want to use the greatest perfect square factor. Square root of 36 is actually 6, so cross that off to show that you actually took the root, and what you're left with is 6 square roots of 3. Let's look at 10. The only thing you can break 10 into is 10 times 1 or 5 times 2. None of those are perfect squares, so they wouldn't do me any good. So square root of 10 is already in simplest form as the square root of 10. Let's look at the third root of 16, and this is where you've got to be very familiar with those perfect cubes. 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, etc. The perfect cube that goes into 16 is 8. So I'm going to break that into 8 times 2. Not a 4, because I'm taking the cube root. Cube root of 8 is 2. So that comes out front, and you're left with 2 cube roots of 2. Here, we'll deal with the negative last. It's just stuck onto the front. I want the perfect fourth root of 162. Well, what are those perfect fourth roots? 1 times 1 times 1, 2 times 2, 1 times 1 times 1 times 1, 4 times. 2 times 2 times 2 times 2. You can go back and look at your table if you wish. 3 times 3, 9, times 3 times 3, or 81. And you notice they get big very, very quickly. 81 does go into 162. So I'm going to divide this into the fourth root of 81 times 2. Remember the negative out front. The fourth root of 81 is 3. So I get negative 3/4 root of 2. Be careful where you place that 3. It goes right up against the radical sign. After that negative. The negative is just stuck onto the front. So this one you've got to be careful how you write it. Now let's look at some that have variables. It says simplify, assume that all variables represent positive real numbers. I want the square root of 16, square root of m cubed. All right, this is how you do variables. 16 is a perfect square, so I'm going to leave it as a 16. If you remember that the variable inside the index, if I raise that variable to an exponential, a fraction, this index is the denominator. So what I want is to get my variable in a form that it's divisible by, its exponent is divisible by that index. So I'm going to bump it down to m squared times m1. Doesn't that still make m to the third? It does, so I didn't change anything. It's still m to the third, but now I can picture this. Square root of 16 is 4. If I change this to be a fraction, it would be m to the 2 over 2, which is just m, so that comes out, and what's left is this m inside. And that is one of the cases where, if we go back to conditions for a simplified radical, the radicand, meaning what's underneath, has nothing raised to a power greater than or equal to the index. So if this number inside the exponent is greater than or equal to the index, then you can pull something out, an actual root. Let's try another one, because I think it takes several times to actually see this with the variables. And then once you do, the variables are easier than the numbers. So let's look at square root of 200k to the 7th q to the 8th. So what I want to do is I want to break down the 200 into a perfect square factor. 100 times 2. By the way, anything that's times 100 is easy. Now, K7, it's not divisible by 2, so I'm going to bump it down till it is, which would be 6 with that 1 left over. That still makes a 7. The Q doesn't need to be changed because that 8 is already divisible by 2. Now I'm going to pull out the factor, or the squares. Square root of 100 is 10. Square root of 2 I can't do, so I have to skip it. K6, that would be 6 over 2, or 6 divided by 2, is K3. That's used up. This K is left over. This Q would be Q8 over 2, which is 8 divided by 2, which is Q to the 4th. What's left under the radical sign is a 2 and a K. It's not a pretty answer, but it is correct. So the number part has to be divided into a perfect square factor. The variable parts have to have exponents that are divisible by the index. All right, let's try this one. Cube root. Negative 8 is a perfect cube, so I'm going to leave that. I don't have to break it down. X to the 4. 4 is not divisible by 3, so I'm going to say x3 times x1, because now it'll be x3 over 3, so that's going to work. y5, 5 is not divisible by 3, so we say y3, y2. That's the breakdown. Now we pull things out. Cube root of negative 8 is negative 2. Cube root of x cubed is just x, because it'd be x to the 3 divided by 3. That's what that would mean if I wrote it as a fraction. This x doesn't have enough to come out. It's got to have at least 3. This y can come out. Y cubed divided by 3, that's a y. This y squared doesn't have enough to come out. So what's left? It's still a cube root, but what's left is an xy squared. Another one. This one has a negative stuck on the front. We'll deal with that at the end. Fourth root. Now I've got to break down 32 into a perfect fourth power, which is 16 times 2. Pay a special attention to this y. 9 is not divisible by 4, but the first number that is an 8. You don't have to go all the way down to a 4. 8 is the first one, and that leaves one y left over. Now we're ready to take the fourth root. Fourth root of 16 is 2. Remember, there's a negative out front. Fourth root of 2 I can't take. Fourth root of y to the 8. 8 divided by 4, y squared. That's gone. This y is left. So what's left underneath is the fourth root of 2y. Again, those take practice.